All right. Today's session is about our DHI PlumeCast application, the marine environmental plume assessment tool for sediment module, as it's in its sediment module. It's meant for sediment plume assessment and forecasting and compliance check regarding sediment plumes. Introduction on me. I'm Sina Saremi. I'm a senior coastal engineer at DHI. I have been with DHI for the last 10, 11 years. I had done my PhD on coastal engineering and specifically on dredging and modeling of sediment plumes in Technical University of Denmark. Day to day, I work also with dredging and sediment plume assessments, both in consultancy and research in DHI, and also doing monitoring and environmental monitoring and management plans for compliance check of sediment plumes in infrastructure projects. I'm also a member of the Central Dredging Association. If you don't know, it's an association for dissemination and collection and basically gathering data and information and events. And basically it's somewhere that you can find all the information, what's going on around the world in dredging. So I recommend you to check it out. And I'm also giving lectures on the course of the International Association for Dredging on Dredging for Sustainable Infrastructure. It's also a nice course and book. I recommend you if you haven't heard about it. So that's me. I'm happy to have you here, and I hope you will learn something after this session. Today's session will be first on our sediment plume management tool. I will go a little on the background and why sediment plume management, and I will introduce you to the PlumeCast product. I will give a little live demo. Basically, I just log into the product and show you how it works. And in the last 15 minutes, we will have a session for the Q&A, so you can ask your questions and we can discuss. So, sediment plume management. Well, if we step back a little, basically when we do infrastructure projects, marine infrastructure projects, in which dredging and reclamation is heavily involved, it can be artificial islands, lands, disposal of sediments in the sea, dredging of the navigational channels, beach nourishment, beach creation, harbor basin creation or maintenance of harbors and navigation channels, and you name it, many things. But in all of them, there is one common thing, and that's the environmental, social, and economical impact assessment, which is important either before the project and also during the project. And also it's important to have in mind that for a sustainable project, this environmental, social, and economical impacts must be taken into account very seriously and in a correct manner. So that's the common denominator for basically all these projects, that you have some sorts of impact or some sort of goal in terms of sustainability or limiting of the impacts or improving the conditions in an area, and you need some sorts of assessment, management, forecasting, and check for it to take place before, during, and after the project. I just mentioned this Dredging for Infrastructure book. It's based on this book. There are like 5 key enablers for having successful assessment, management of the impacts, and make sure that your project goes according to the plan, fulfills the sustainability goals, and so on. And those are what? Those are during the design of the project, you have properly examined the different options and all the scenarios possible, and have chosen the right scenario and option to gain the maximum, benefit in terms of sustainability, in terms of limitation of the impacts, and basically final goal of the project. Be able to value what kind of environmental gain, for example, the project provides. To be able to identify what are the stressors on the environment, for example, that this project is causing, and be able to assess them and control them. And of course, you have a lot of uncertainty in the beginning of the project, especially, and how do you deal with those then during the project, how you are prepared in terms of you have already taken into account different variations and scenarios, and you have some sorts of forecasting in place that you can forecast the risks and be able to identify them before it's too late. And finally, should be able to, during the project, be more adaptive, be able to adapt to the circumstances during the project, be able to tackle the risks and forecast, for example, say some non-compliance that can happen, or that the design is not as expected, or the environment is not reacting as expected. For example, I can name several nature-based solutions that are heavily based on, say, uncertainties and scenarios that you are dealing with the nature. And nature, sometimes when you go in place and start the work, you realize that the soil is not as we expected, the mangroves are not reacting or affecting as we expected, or so on. So that adaptability during the project is quite important. So these are, say, the 5 enablers or important points that one should take into account when dealing with these sorts of projects. And one of these environmental stressors that I mentioned is turbidity. It's quite common stressor. It's used a lot for impact assessment. You use turbidity to check if this project is impacting the environment or not, because turbidity is a direct result of the spillage of sediment from your dredging or reclamation works, and it impacts the environment directly or indirectly by creating shading, or by covering the habitats in the sea, or by molesting the, say, recreational areas, or basically dispersing contaminations to other places. So turbidity, or basically sediment spill, is one of the most common stressors that is usually used to evaluate the impact of a project. And how is that done? Mostly by models. So you use models to basically simulate how this spillage of sediments transports into the sea, into the water, the dispersion, the deposition, and the final destination and fate of these sediments, and how they impact the surroundings. So this is very important in terms of, say, knowing what kind of, say, impact your project is going to take to create. And as you can see in these pictures, the sediment plumes can come from a spillage of the barge, from disposal of sediments into the sea, and quite sophisticated, say, near field and far field processes take place. So it's important to have a good understanding and grip on these processes to be able to simulate and model them correctly. Another little image of this book, I use it a lot, and I recommend you also. So models, basically sediment spill models. Now we are down to this sediment spill. Is used in several phases of the project. It's not just in the beginning. Of course, in the very beginning, you have the EIA phase, the environmental impact assessment phase, that you use the models to understand the impacts. Like you assume some sort of dredging activity, you assume some level of spillage of sediments out of that activity. You then identify where this sediment can go and which receptors, we can call them receptors, or receiving, say, habitats, could be flora, fauna, could be any sort of other types of receptors, how they receive this plume and how much impact they receive because of the concentration of the sediments arriving by sediment plume. And that's where you establish, say, the impact that this project can have. You have minimum details. You don't have enough information at this stage, so you base your work on a lot of assumptions and uncertainties and safety margins. Then comes again models in play when the project wants to start. Over there, then the impacts are identified, the acceptable levels are identified. Now, for example, the designer of the project or the contractor wants to identify what type of machinery and dredging work I should use to be compliant against these identified impacts. So you go the other way. Now you know the impacts. You use the models to see what type of dredging machine, what type of schedule or seasonal work will result in minimum impacts in comparison to what has been identified in the EIA. So that's another way. But here you have a little more details. You know exactly your machines and you know your schedule of the work and so on. So you increase in details, a next level of model is used. You have models again in the very end or in the operational phase of the project where the project starts. Now the dredgers are on the site, they are dredging, they are reclaiming and moving around the sediments, the spillage is taking place. Now to control the impact and make sure that the project is compliant, you start to use the models in an operational way to basically document, register, and control, and observe and monitor the sediment plumes that are being created in real time. So it can be like the forecast models that help you to, okay, now tomorrow they're going to dredge so much based on the forecast model, the plume going to go there. It seems to be okay based on the EIA limits, so we move forward. Or no, the forecast model says that you're going to be non-compliant tomorrow or the next week. So change the dredging pattern or take into account what other mitigation methods can be done to avoid that compliance. Or basically use the models as a nowcast to simulate what's going on, because you have limited visibility on the site in terms of impact control. You have maybe a couple of turbidity sensors, which are just point measurements in some sensitive points, but you don't have the big picture. By a model, it can provide you, if it's a nowcast model that can basically simulate what's going on, you can have the full picture of where the plume is ending up and what levels of concentration is giving to you. And that is another way of using models, say, in operational mode for compliance monitoring. So as you see, models are used in all basically phases of the project in different levels of detail and with different purposes. So basically we said that we need the models and they are everywhere in all sorts of phases of the project. And that's basically is the topic of today, that we need these model simulations in different phases of the project to be able to understand the impact, especially in terms of sediment spill and dispersion of sediments. So it's a challenge. So you need to be able to do these simulations for planning scenarios, as I mentioned. You want to do planning of your project, the design of the project is a nature-based solution, so you need to get a lot of scenarios, or it's just a standard construction of, say, infrastructure, and you need to be able to check the different options and what levels of impact they can create. So you need this kind of modeling different scenarios. In operational phase or also during the EIA, you need to be able to predict the sediment plumes, where they go and how they impact the environment. So that need is always there. Then you have during the real time and operational phase, you need again models for forecasting, for nowcasting, for monitoring the impacts of the projects connected with, say, sensors on the site and so on. So these needs are there, and it's a challenge sometimes to gather them. It's expensive, time consuming, and so on. So that's the challenge that we would like to tackle, and that's where we have been engaged in developing the tool PlumeCast, which is useful for basically all the stakeholders involved in such projects: authorities, advisors, consultants, contractors. And it's basically by providing these services to these stakeholders for different purposes, as we mentioned already, like would be screening and pre-evaluation, adaptive management during the project, forecasting, time windowing of the activity, site selection, compliance check, you name it. So all of these in different phases of project, basically they need some sorts of model, and we have try to develop this product that can bring this much more easier and more accessible to the user of it. So this product helps basically by providing the models to a more easier accessible to the users, to make the decision making much faster and more efficient. To be able to go do all the regulatory compliance, quality assessment of the environmental impacts during the operation, to be able to report, say, the compliance on a daily or weekly basis with the latest model results, and share the information easily, rather than waiting for a modeler to finish the models and create a report, send a report to someone and someone else. It could be more accessible just via a click online. Then the product makes it much more easier to use a model, so you don't need to be like a software specialist of the X and Y model to be able to use that say option. You can still do your plume dispersion analysis, but without really being expert of that specific modeling software. And of course, since we have been developed this product and we are behind it, we are always there to support and give guidance in this field. So to summarize what this PlumeCast solution brings, it's basically a web portal that you can execute models, access model results and analysis directly. It's based in the cloud, so there is no server in the basement. There is no software machine required. So everything is basically hosted on the cloud, on our cloud system, and you can access it through a browser. You don't need anything else on your laptop. We are doing plume dispersion analysis, and I have to clarify that plume dispersion analysis, it's always requires a local specialized model for that project, for that area. We cannot use universal global models that are one fit for all. The computational model, the computational mesh used for that model, they're all always site-specific, project-specific, based on the condition in the area and the requirements of that specific study. They change. So that's why it's important to keep in mind that there are always one specific model made for that project area that sits behind the system. Otherwise, it cannot provide the right precision. Software used naturally is mic FM, both in 2-dimensional, mic 21 or mic 3 in 3-dimensional, are accessible via the system to simulate the plume dispersion. It combines the hydrodynamics and waves, the currents and waves, especially waves in a more coastal areas, that the waves can have an impact, especially when they are breaking and filling the seabed. They can have an impact on the sediment plume dispersion and deposition and resuspension. So therefore, both are important, currents and waves. It can be used as a hindcast system. So you can do all your, say, scenario analysis, impact assessment analysis on a specific period in the past. Mass production of different scenarios and design options. It provides, say, the fate of contamination. Also, if the sediment has specific types of contaminants attached to it, it can basically track those also and provide, say, the fate of the contaminants that were attached to the sediments when they are released, say, due to the spillage of sediments from the barge or during the reclamation works. As I mentioned earlier, the models can be set as a forecast model, so they connect to a specific, depending where in the world you are, in the forecast system that will, say, update the model to provide information for the next, so you can basically run sediment plume scenarios for the next 7 days, 10 days, and specifically used and it's being used in a lot of monitoring projects, these sorts of models that are helping the operations to be more proactive in terms of checking the impact instead of waiting for the impact to happen and then act upon it to use some forecast system to predict the next week's operation and make sure nothing is going to be exceeded, and like that you minimize the impacts. And as a platform online, it will help. It will show also you can connect to live data from say where are the vessels moving now, where is the sensors are sitting now, what kind of information we are receiving from the sensors. If we can connect to a satellite image to put it on our map to check what's going on. So all that can be available again, being an online platform. So as I mentioned, it's a web service. Here on the right, there are some snapshots of how the results could be visualized, for example, for a sediment plume scenario. It provides the maps, typical maps. In the live demo, I will go more in details to show you of the sediment plume maps and the time series and of the concentration at required points. So, and that's all view a couple of clicks and easily accessible and downloadable, all the results and information. So makes all the modeling journey much more accessible and easier and faster, especially if you are dealing with a lot of projects and not everyone is an expert in the modeling and you need to do things fast. So the interface, instead of having the complex interface of a software, numerical software that you need all sorts of inputs and keys and clicks, it's more streamlined towards sediment spill analysis. So what you need in sediment spill analysis, you need to know when the dredging happens, where the dredging happens, and what type of sediments are involved in that dredging work. So that's why it makes it much more, easier and more understandable for everyone in the field, in this field of work. You can set the sediment spillage, the source, the location, the amount of dredge rate, for example, the production rate of the machinery. And for example, you can also provide some silt curtains. Oh, I want a silt curtain at this stage here and here to see how it can impede the dispersion of the plume, for example. And that's it. The rest is taken care of behind the scenes, and it runs and it provides you the results. As I mentioned, during the operational phase of projects, this product can be used as basically as a decision support platform, because it can bring all together the model results, the plume that the model shows, for example, live access to where the dredging vessel is moving during this period, for example, where is my sensor is sitting now, what is the sensor reading at this time, what the model has predicted. If it's the compliance check is based on some thresholds, and that should be say for you typically is like a warning, or then you have like a stop criteria and so on. Then kind of a traffic light can be set up in the project that based on different trigger levels and based on the concentration or turbidity, they can change the color. So basically the user or any stakeholder can log in and check, okay, are we compliant? What is the compliance criteria at this stage of the project? Where is the monitoring buoy sitting, for example, here in this map? Where is the dredger at the moment? It has been sailing this route to the disposal site and back, for example. And what are the readings of the monitoring buoy at that time? So it brings not just the model, also a lot of other information into play in the same place, and helps a lot in terms of transparency and efficiency in communication during these types of projects. Having a map here, it also allows to change the background to the latest satellite images and so on. So it suddenly turns into a very strong DSS system. Yeah. As I mentioned, it's basically a system that has the model at the same time receives data from the vessels and the buoys, and will then propagate the information from the same portal to the relevant decision makers. We have an example. You can find it online. It's a case study where we use this system that is published in the WOD conference, World Dredging Congress, a couple of years ago. And if you're aware, this year we have the Dredging Days conference in Belgium. And over there, we're going to present another case study again. And yeah, that will be also available of the use of this system. Yeah. And as I mentioned, it's based on cloud. We use Azure, Microsoft Azure cloud system to host and basically do all the model simulations, storage of data, access, and all basically everything that this system is based upon, say the Microsoft Azure and all the security around it. So, in summary, this PlumeCast, which enables you to do modeling in different phases of project much more accessible and much more easier during the operational phase, can provide you as a decision support system, can be used in many types of project, all sorts of dredging operations, if they need such analysis, environmental compliance, if you have to do permits, to run several scenarios for giving a permit or seeking for a permit, you need to show compliance. So this system can be used. Any sorts of ecosystem protection and nature-based solutions also are, especially when you have to do a lot of scenarios, a lot of analysis, and things should go fast, and not everyone is a software expert, then having a model that is so easy to prepare and run will help a lot. And finally, of course, during the operational phase of the project, where you need forecast system and monitoring of the situation, again, this system can be used. All right, now let's go to see how the product looks actually. Will be some limited demo that I will show. Yeah, so basically it's the product starts with like a project management where you can define several projects. Because if you are dealing with several different projects, you can basically define them here. Up here you can see we have like a sediment spill module and then the ecological spill module. Today we are talking about the sediment spill module. The ecological spill module, which is a similar application but deals with, say, outfalls where wastewater or other sorts of discharges are being released into the sea, in the marine environment. And basically plume dispersion on that side of the contaminants and so on, the bacteria and heavy metals. That's the ecological module that we already had a webinar for it back in December. And if you look into our website, you can actually find the recording if you are interested. But today we are focused on the sediment spill module of the product. So you have your projects here. Then in each project, you can have several scenarios. And basically, these scenarios are the models, right, you have been running. So you basically, then you say, add a sediment scenario, then depending which models you have access to, in this example, like this user has access to 2 different domains, and the model are in hindcast mode for planning and for impact assessment. So it's not a forecast model, otherwise these dates would have been now and future. But these models, they have like a fixed period for planning purposes and for typical impact assessment studies that you do modeling in a specific period in the past, depending on seasonality and so on. They can be shared or private. If it's shared, so basically your organization, if you have access to this product, then your colleagues, they can, if they log in, they can see if it's your scenario is shared, they can see your scenario and look at your results. And that's very useful when you want to share the information and for different stakeholders of the project. But if it's private, then it's only you as a user who can see your results and your scenario. The model can be, then the scenario or the model is basically can be ran during the available period of this specific model. In this demo, we have a model that is for 4 weeks, and you can run a scenario only for 1 day or 4 weeks, or what is needed in terms of the analysis you need. Then here is the next step is basically to set up your spill. Let's say I want a dredge rate of so much with such a percentage of a spillage of sediment, and it's either is a complex dredge plan that you can upload a dredge plan in the format of say a CSV file that can be loaded up, or in format of a mic, which if you are familiar with mic, it's the FF0 file, which is a format that accepted with mic. So the user, if it's a mic user, can basically use a DFS0 uploader. Or otherwise, I want to just create it manually, my dredge plan. And basically, we can put it as a moving, for example. And for example, is a dredger that is dredging this channel during this, so this distance during the time that we decided for this scenario. Well, this is a very simple way of setting up a dredging plan. If you don't have already prepared a more complex Excel sheet, for example, to upload, and what percentage of sediments are going to be spilled during this dredging track. So very simplified version of setting up dredging. We can also add maybe say there's a TSHD, that for that TSHD I have prepared a dredging file. So basically it can be several dredgers. This one is a backhoe dredger, this one is a TSHD. So yeah, the type of dredger is important in the model, that how the spillage happens in the model. As you know, TSHD, trailing suction hopper dredger, the overflow is the main component of the sediment spill. So it's overflowing from the barge into the sea. The backhoe dredger is the one that basically, while raising the sediment from the sea but out of the sea, will release some spillage while coming out of the water column. So all that is taken into account when you select the type of dredger. The disposal is basically a split hoppers into the sea, the placement of the sediments. So a little more information is needed in terms of the size of the barge and how it opens. But again, if you set it as a manual, then you say, okay, the disposal place, for example, is somewhere here. You have access to some shape files that you can turn it on and off. You can load them in the project area. And you can basically set the disposal and say it's a frequent disposal every 4 hours with such a volume, and relevant information that is needed, and the location. So that's the manual way of setting up a disposal plan. Otherwise, you can always also load basically the disposal plan as a file. As I mentioned, it is possible to also design sealed curtains. So it's basically, you can say what's the efficiency of the sealed curtains are not 100% efficient. If you have ever deal with them, you know they are not perfect. Either they tear apart or they are not perfectly closed. So there are always some leakage happening, and that leakage or that risk of leakage is reflected in the model as this efficiency number here, and is a floating sealed curtain. So especially so it moves up and down with the water, and the curtain height then is basically from the surface of the water downward. This is the type of sealed curtain we have available now here. Of course, we have bottom mount sealed curtains. We have different types of sealed curtains, but here we have so far included only the floating sealed curtains from the surface downwards. And basically, again, is a very simple manual way of designing your sealed curtain. For example, if it's a nature protected area that you want to protect from the plumes to not to reach there, or you want to check the design of your curtain on this side or that side, the size and so on. So you can basically use this feature here. I have to mention that when you put a sealed curtain in, in a model, you are basically blocking the currents. So that means the model will update all the hydrodynamic analysis when you set a silt curtain in, because it will block the currents. So it's not just the sediment that are moving, it's also the currents are now changing. Because I have to mention that the models we use to be faster, they are usually once this hydrodynamic is done once, and then the sediment analysis is done on top of it as a decouple. So it goes uses the hydrodynamic during this period, and then you can run several scenarios of sediment dispersion on top of it. So you don't need to recalculate the hydrodynamics again and again, because the hydrodynamics are the same. The currents are the same here during this period. Is your sediment spill that is changing. For example, you put a spillage here or there, or with a different amount of sediments or different amount of clay in it, this time less sandy, more sandy, and so on. So in that sense, to benefit from that, we make the models faster. We usually re-execute the hydrodynamic once, and that's it. Then all the analysis and scenarios are done on a already made current fields. But if you suddenly set a silt curtain, then that changes. Now we have to re-execute. So that's why with the silt curtain, the models get slightly slower to finalize, because they have to recalculate the currents. Then at the results section of the product, where you want to see what you want to see out of this analysis, okay, the typical plots of the average suspended sediment concentration, the maximum suspended sediment concentration, and say the duration that suspended sediment concentration exceed, say, 20 milligram per liter or 100 milligram per liter, depending on the environmental criteria or the maps that you have to report out or check. Then it's typical that there are some limits provided or known in this area based on the type of receptors and type of the, say, criteria of the environment. Say the duration, for example, that the concentrations in the water are above 20 milligram per liter is important. It should not exceed 24 hours, for example, or 6 hours, and so on. Because that's, for example, the level that, say, the flora fauna in that area can tolerate. And more than that, they will be molested. So that's, say, the exceedance levels that you can set as many as you need. Then by default, all the maps are made on the total amount of suspended solids in the water. But sometimes if it's relevant to only check the, say, the clay concentration or only the fines, then you can basically go and say, I want also extra maps, but only for my fines, for example, not the total, but I want the fines maps also to be analyzed and produced for me. Then you can also set a monitoring point, we call them, basically time series, extraction of time series of the suspended total suspended sediment concentration at a specific point. And I want, for example, the concentrations 3 meters above the seabed, if that's the case. Then basically you can say I want the extraction to be, for example, if the dredging is happening here, I want to see what are the time series concentration of the sediments inside this bay, for example. And that's where you want to check how the concentrations are changing. In dredging projects, sometimes is relevant, is typical that you work with the spill budget or the amount of spill that is leaving the area, for example, or the amount of spill entering an area, or the amount of sediment that is leaving or entering. So that flux of sediment is relevant and important, and that you can basically get by adding, we call it a monitoring line. It's basically you design a line and you get the discharge either instantaneous or accumulated across that line, for example. So it's basically saying that you want to check, for example, the flux of sediment that crosses this opening, or as an example, or it can be many other places. But this basically provides you a time series of flux of sediment, either instantaneous flux or accumulated flux time series, discharge time series, or across the line. It's relevant in such projects usually. So basically that was it. You set your dredging, you put your disposal, in case mitigation, what analysis I need, what plots I need, and That's it. Then it's basically ready to run. Now, here we have some already made results, for example, we can look at. So here we have three types of results. We have the animations, which is actual model results during this scenario period at each time step. We have the statistical maps, like the mean, maximum, exceedance, and finally the time series extractions. So then if the model is three-dimensional, then you have access to the surface plumes, the bottom plumes, and the depth average plumes. If its model is two-dimensional, then you have access to basically depth averaged. And these are basically just the raw model results, the concentrations, depth average in this case, at each time step that the model goes. So this, in this case, there was a dredger in the channel and it was a disposal site out here, which the depth average concentration looks something like this at each time step as the animation goes forward during this scenario period. All these maps basically can be downloaded as a shapefile. Sometimes it's needed to load them in another GIS platform or just as in a report. Since the model also has the currents in it, so we can also visualize the currents as vectors representing the current directions and relatively the current speed by the size comparison. So these are the concentration fields. Then the deposition or the bed thickness on the seabed, like what has been deposited at each time at the end, for example. As we can see, not much here, everything has been flown away. We have like 1 millimeter of thickness maxima, so it was not a successful demo in this case. Then, yeah, another type of way of looking at deposition is the per square meter deposition in terms of mass, not meters, not volumes. So here is basically showing the how many grams per square meter has been deposited, and since it's been very small, there's been less than 50, so that's why it's invisible on these results. Then comes the statistics maps, as we saw in the scenario design. So it's basically the mean total suspended sediment in the bottom, for example, close to the seabed. It's much higher, of course, and then the depth average, the mean total SSC, which is like much less. And if you average around the depths here, it's not much seen. Duration plots, similarly above 20 milligram per liter, for example, at the surface. So it has been maybe less than a day. It has been exceeded 20 milligram per liter if changed into hours at the surface. You can see it's 1 hour. If you go depth average, then it's of course much longer periods that it has been above 20 milligram per liter. So that's the typical statistical maps that the product provides. And finally, the time series that in this case, we have extracted the concentration at this point. And also the current speeds can be extracted at that specific point and the current directions. And these are again all downloadable either as the raw data as Excel or the PNG for reporting and so on. So it's a very typical standard results that can be seen and used. But of course, is something that a specific user needs additional plot, it always can be added. It's not a rigid product, so it's not always you need maximum and duration time. There are a lot of projects that they need a specific type of plots in terms of statistics, especially, that is relevant and needed to be produced. Yeah, that's all. And see, our little example is about to start now. It's going on. So that was the live demo. So you could see how the product looks like and how it can be used.